Okay, hello everybody. Today I'm going to be covering what I consider to be one of the truly most magical data structures called splay trees. Now that we've had a chance to exercise a little bit with potential functions, we're going to see some of the real power of potential functions, but also some of the real black magic of potential functions, of sort of how in the world did they come up with that moment in this presentation. So let's get started. So what are splay trees? So this work appeared in a paper called Self-Adjusting Binary Search Trees, which appeared in the top journal, the Journal of the ACM, in 1985. And it's by Slater and Tarjan, of course. How could you have a data structure without Tarjan? All right. They actually describe this data structure as a data structure that plans ahead. But I don't see it that way. In my mind, it's really following exactly the same procrastination, laziness approach as the data structures that we've seen so far. And hopefully by the end of this lecture, you'll agree with me. And so the title describes what a splay tree is. It is a self-adjusting binary search tree. So of course, we all know what binary search trees are. Don't need to talk about those. And we introduced them very early on in algorithms as a way to store a set of items and do searches under equality or predecessor or ancestor queries. And they work great if they are balanced. Right? And so I think the usual way these are, the usual way we experience these is that first we see binary search trees and we sort of learn about how to do the search operations in them, and that's all really nice. And then we say, well, if they're balanced, then those search operations are fast. And then we sort of say, and in the next class, you'll learn how to make them balanced. Right? And so then we study various ways to enforce balance in these binary search trees in order to get good search behavior. And there are who knows how many different variants on the binary search tree for balance. We've got red-black trees, which we talked about yesterday, or on Wednesday. We've got AVL trees. There are these things called scapegoat trees. There are 2-3 trees, which are, it turns out, are sort of another way of looking at red-black trees as if they were sort of like B-tree data structures. The list goes on, and sort of all these data structures that work to keep the tree balanced. Okay? And they do this by maintaining some extra state at each node, describing the level of imbalance of the binary tree. And when they see that the binary tree has gotten out of balance, they do something in order to rebalance it, and they update their tracking state. Right? So we've all seen this. So splay trees discovers that none of this is necessary. The splay tree is a balanced binary search tree, with quotes around the word balanced, which maintains no state except for the binary search tree itself, and nonetheless is able to achieve as good search performance as a binary search tree that carefully balances itself all the time. In fact, it can even outperform them in various ways. If you imagine having extra information, such as information about the access frequencies of the items in the binary search tree, you might want to be clever in building your search tree and put the frequently accessed items at the top so that you can get at them faster. Well, splay trees don't try to do that, but they are as good at finding those items as a search tree where you have carefully put the commonly found items at the top. So they're quite a remarkable data structure, despite having no state at all in them. Okay? So how do these splay trees work? Well, they are lazy. Okay? So So if we take our lazy perspective, let's think about what we might want to do with binary search trees. So if we're going to do a lazy balanced binary search tree, then when we insert items, the thing to do is not bother balancing, right? That can't be lazier than that. You just insert in the usual fashion. And that is, roughly speaking, what splay trees do. But as with the other data structures, we now have to worry about if we were lazy then, we may have to pay for it later. And we're going to have to explain how we can justify searches that take a long time because we didn't prepare for them in advance. And we're going to justify for that. We're going to justify that using a potential function. To analyze our searches. And we're going to explain how searches that take us a long time lead to simplifications of the data structure, which allow us to take less time on the searches later on. Okay. We essentially, through that potential function, use the work of the searches to pay for the rebalancing that we're going to need to do. Okay. And as I said, the potential function itself seems kind of black magic, but I think that if we work with it a little bit, we'll start to develop some intuition about why splay trees do what they do. And in my mind, there are sort of two related intuitions that are worth pursuing. One is path shortening, and the other is rebalancing as things that the splay tree is sort of carefully trying to do. So let's talk about path shortening first. Okay. So as I said, splay trees don't try and stay in balance. Instead, they wait until you do a search that takes a large amount of time, and then they fix the data structure because of to pay for the work that they just did. So what does that mean in a splay tree? It means that if a search is long, then we should shorten the path that we took on that search. Okay. And the idea is that somehow this shortening should release potential to pay for the work that we did. So if when we traverse a long path, right, the real cost of that is large, but if we can then make the path shorter and by doing so release some potential energy, we can use that potential to pay for the real work that we did and end up with a small amortized cost. Okay. The problem is that shortening one path makes others longer. Right? Because the way you're going to shorten a path is by moving things onto other paths, and they're going to get longer. So we're going to have to be careful in the design of our potential function to make sure that we do get something back when we shorten this long path. Okay? But now let's instead talk about the other intuition, which is rotation or rebalancing. And let me get at this by asking a kind of odd question. Why is search fast in a balanced binary search tree? So, you know, we have this sort of ingrained now that if you have a balanced binary search tree, search is fast. Why is that? Yes?
Because the height is limited by log n. So.
Okay. So your answer is because the longest path is short. But that's not actually the definition of a balanced binary search tree, right? That is something that we take as true in a balanced binary search tree. But why is it true? Yes?
They're all the same length.
So they're all in a perfect binary search tree, all the paths to leaves are the same length. But the notion of a balanced binary search tree that we try to achieve with, say, a red-black tree or an AVL tree does not attempt to maintain perfect balance over all of the leaves. Instead, it sort of aims for a rougher notion of balance, which is still good enough. Yes?
The two subtrees are at most difference of 1.
OK, so that's the answer I was looking for, although I want to refine it a little bit. So it has to do with the relative sizes of the two subtrees, right? And so these relative sizes are close. And I say close because exactly how close they are depends on exactly which kind of balanced binary search tree you're implementing. So in some, they try and keep it within 1, right? But others are more relaxed about this. And in fact, it is sufficient for each to be a constant fraction of the parent. So for example, I might want to aim for a, at worst, 1/3, 2/3 split. In other words, both sides have at least 1/3, both sides have at most 2/3 of the children of the root, or of the parent. Okay?
The depth is within a factor of 2 rather than number of children. Otherwise, it could be like, 1/3 in the line here and 2/3 in the line here.
So that would be true if I was only preserving balance at a single node. But if I enforce this balance condition at every node of the tree, then I'm in good shape. And let's understand why I'm in good shape, right? So why is it, so you're absolutely right if I only look at one node. But if I can say that every single node has this balance property, why can I infer that the tree has short searches or short paths? Yes?
At every step, worst case, you shade all the constant fraction of the search tree.
Good. So on descent, so the consequence of this is that on descent, each downward step reduces the number of descendants of your current node by, say, a 2/3 factor. And therefore, within order log n steps, you have one descendant. So this is sort of the fundamental concept of divide and conquer, right? That if you can divide well, then you can conquer quickly. Right? So now that we have this in mind, I can ask, when search is slow, what's wrong? All right, so really, I'm just asking the contrapositive question here. So if we have a search tree and it's slow, there's a long path, what can we say about the problem of that tree? What was that? Sorry?
It's not balanced. It's not balanced.
It's not balanced, but sort of what does that mean as we go down node by node when we say that it's not balanced? What are we saying is going on? Yes?
We're not eliminating the number of nodes that's proportional to n, but rather constantly.
Good. So what's going on? The reason that it's taking us a long time to search is that when we go from a node to a child, that child is fat, right? It has a lot of the children of the parent. So basically what we can say is that the source of our problems is fat children, right? And fat children are bad, okay? And everybody in America knows this and is working hard to address the problem, okay? But, I was one of those kids. I had to go shop in the Husky section when I was getting ready, when I was getting my bar mitzvah suit and stuff. And so I would like to phrase it slightly differently with sort of a better perspective. What I'm going to say is that fat children have potential. And again, this is what the parents will always tell you, right? Okay, right now he's sort of a lump, but he has potential, okay? So this is the perspective that we're going to explore for this data structure. And so the idea is going to be that if we are descending, if we're taking a long time to search, if we are encountering a lot of fat children, then there's some potential available. Of course, in order to recover that potential, we're going to have to destroy the fat children, okay, to release potential. Okay. So that's sort of an E equals MC squared kind of thing. And so this potential that we're going to release by destroying the fat children is going to cover the cost of the search that we just carried out. Okay. So let's start to fill that in. Okay. And, well, actually, this is a little harsh, right? So let's not destroy them. Let's just promote them. Okay. So the real source of potential is going to be a fat child that's very low down in the tree. And the way that we're going to correct that problem is we are going to promote that fat child up to be high in the tree. That's going to release potential. The child will still be there, will still be fat, but now that it's high up, it won't matter. Okay. All right. So how are we going to do this sort of promotion? Well, we're going to think about rotations, right? This is the natural primitive operation that you perform in order to balance binary search trees. Okay. And so what's the obvious thing to do? If I sort of take this perspective that, right, we sort of, a fat node, a node that has most of its parents' children is a bad thing to have so low in the tree. So what should we do in order to address that problem? Well, we should move that fat child higher up in the tree. And we can do that through a series of rotations, right? So a standard rotation would take something that looks like this. Here's X, A, B, C. These capital letters are subtrees, and then we have these two nodes, X and Y, and we would rotate the tree while preserving all of the order relationships. And this brings X up, right, and pushes Y down. Okay. So we can argue, right, if X is fat, right, most of the descendants are over here, then this rotation may improve things by moving a bunch of the descendants over to the right and hopefully giving you more balance between the left and right subtrees. Now, of course, if all of the weight is in B, it's not clear you've gained anything, right? And that's not just a function of this particular picture. Nobody has really figured out how, from the splay tree perspective, to make these single rotations work. Okay. Instead, splay trees use what are called double rotations. There are two kinds of these. Well, I'll come back to why these are arguably better. But there are two types of double rotations because now you actually think about the two steps in your tree. And so I can draw you a collection of an X, a Y, and a Z. Here we have two children, A and B, C, and child D. Okay, so now we're thinking about three nodes altogether. And we can do a so-called zig-zig double rotation. Sorry, that's the technical term. I didn't make it up. I have to use it. Which creates this structure. Okay? And you'll notice that the zig-zig, just like the single rotation, is bidirectional, right? You can unzig, or you can undo a zig-zig with a zig-zig in the opposite direction. But the really interesting one is what's known as the zigzag. Okay. which is what you do when your 3 nodes are sort of going back and forth instead of being in a straight line. And a zigzag relationship rebuilds the tree. Whoops. As follows. Okay. And the zigzag relationship is one directional, right? It produces a tree that you wouldn't want to zigzag on with those 3 nodes. And the zigzag captures, I think, some of the intuition about why these double rotations are better than the single rotations. Because this zigzag operation has actually made the tree shorter. Right? So over here, we had these length 3 paths to B and C. But after the zigzag construction, B and C are only at depth 2 from the root. Okay, so there is some path shortening going on. Again, this is somewhat deceptive because A, B, C, and D can be whole subtrees. But I think that it's a useful intuition. Okay. So these rotations, you sort of point at a node and you say rotate this node upwards. Right? So this is a single rotation of x that takes it to its parent. This is a double rotation of x that takes it to where its grandparent was. And so is this, a double rotation of x that brings x up to where its grandparent was. And so the rotation is defined just in terms of which node is going up. And it affects that node and its 2 ancestors. Okay? Its parent and its grandparent. And so that allows us now to specify the incredibly simple implementation of splay trees. Okay. And so I'm actually going to, for the time being, ignore insertions. Okay. We're just going to talk about the process of searching in a binary search tree. So I'm going to assume that I've already got this binary search tree which has n nodes, and I just want to perform a sequence of searches in it. At the end, we'll come back and take care of insertions. But so the search procedure is you do the normal search procedure, and then you splay, and I'll explain what that means, the found node to the root via double rotations. And one final single rotation if necessary. And that's the entire splay tree algorithm, complete with its balancing algorithm. Okay? So there's no state, there are no bits in the nodes or anything like that to keep track of the balance of the tree. It's just that every time you do a search, the node that you found gets dragged all the way up to the root through this series of double rotations, and that's it. And the claim that we're going to spend the rest of the lecture proving is that the result is as if your search tree were balanced. Okay? Yes?
How do we pick whether to zig or zag?
How do you pick what?
Whether to zig or to zag.
So that the question of whether to zig or to zag is determined by the structure of the tree above the node that you want to promote. Right? So if you have two children in the same direction, you're going to do a zig-zig operation. If they're both left children, then you go this way. If they're both right children, then you go this way. Right? And if they go in opposite directions, then you're going to do a zigzag operation. Okay? So there's no choice there. It's just determined by the structure of the tree. Yes?
The question might be stupid, but when we do those rotations, we destroy the order between.
No, so that's exactly, that's actually critical and worth emphasizing, is that this rotation does not change the relative order of nodes, right? So let's think about this, right? So let's look at the single rotation first. Okay, so the relative order determined by this search tree is that the stuff in A is all less than x, then we have the stuff in B, which is between x and y, and then we have the stuff in C. Yes? And that's the order that is implied by having them in this arrangement in the tree. Well, after this rotation, it's exactly the same order. The stuff in A is smallest, followed by X. Then the stuff in B must be between X and Y. Then there's Y, and then finally there's the stuff in C. Okay? And the same can be seen, the same is true of these double rotations, that they do not change the ordering that is implied by the search tree. Okay? And then that's crucial, right? If we change the order, we would lose items. Okay. All right. So what's interesting about this is that after you do a search for the item that you searched for is at the root. And that's why it's called a splay, is that you've kind of rearranged the tree to split the items with everything less than your search key on the right, and everything less than your search key on the left, and everything greater than your search key on the right, and your search key is in the middle. And that's actually quite useful. You can use that for a number of additional operations that I'll describe at the end of the lecture that splay trees can do very efficiently. Now, the access theorem. This is where I tell you that splay trees are fantastic. Sort of all of the wonderful time bounds that follow from splay trees all follow from this single access theorem. So we are going to define, let Wi be a set of arbitrary weights on your nodes. So each node slash key gets a weight that you can pick. It should be positive, I guess. I don't know what happens when you use negative numbers on your weights. And once we have these weights, let's define the size S of a node X in the tree to be equal to the total weight of descendants of node X. Sorry? Including itself, yes. Just like last time, descendants includes yourself. And now we define the rank R of X to be equal to the log of the size of X. So now every node has a rank. And finally, reaching into my black hat, I pull out a potential function, phi, which is equal to the sum of the ranks of the nodes. Where did that come from? Who knows? But I will tell you that when I was a graduate student, I was sort of picking over my desk, and I found in the bottom drawer all of these funny drawings of trees and weird numbers on them and stuff. Turned out that that was Danny Slater's desk when he was a graduate student working for Targin. So I have this nice little connection to this data structure. What was that? It actually connects to entropy in a sense, again, that I'll get to towards the end when I look at some of the applications of this. But let me at least try to give you a little bit of intuition about this potential function phi. We'll get some more of it later, and you'll see some more on your homework. But the intuition is that having a deep fat, as we said, a deep fat subtree is bad. In other words, if we have a deep fat subtree, that's something that's contributing to these long searches, these long paths. And so we should associate that with a large potential so that then when we do away with that deep fat subtree, we get back the energy that we need to pay for the bad search that we just did. So this should imply a large potential. And I claim that it does. So why does having a really large subtree deep down in your search tree produce a large potential under this metric? Yeah?
It contributes to the size and the rank of all the potentials.
Exactly. You'll notice that a subtree, especially a large one, contributes to the size of every ancestor of the subtree. And therefore it contributes to the potential of every ancestor of the subtree. So if it's large and deep, then it's contributing a lot of potential to the system. Okay? And if we bring it up, then that potential contribution goes away. In other words, we recover some potential that we can use to pay for having to go find that large subtree. Yes? Sorry? This is what's remarkable. The weights can be anything you feel like. And in fact, we're going to prove 3 different powerful results about the access capabilities of Splay trees just by making up different weights. Whatever we want. That's what I'm saying. We're going to prove, right, you'll see the applications of this, but they don't have to stand for anything. Or sorry, depending on what you want to prove, you can pick them to stand for something useful. You set those weights, the access theorem gives you a result for the searches. Okay? Okay, so sorry, I've defined some background, but I still have to give you the actual statement of the, I guess, I don't know, maybe they called it the access lemma. I certainly consider it a theorem. It's pretty amazing. The claim is that using this potential function, the amortized time to splay a node x anywhere in the subtree, given root t, is order of, or sorry, is at most 3 times the difference in rank between t and x. Plus 1 for the single rotation you may have to do at the end, which is therefore order of the log of the size of the root divided by the size of x. Okay. And so before we do anything with this, before we go off and prove it, let's look at an immediate application.
Any weight size.
For any weight system, for any set of weights.
So I can't say all the weights, all positive stuff.
All positive weights, that's right. So let's start off, let's suppose that we set all wi equal to 1. Okay. So what does the access lemma tell us? Well, we have to break it down, right? So in order to compute this bound, okay, you're claiming an order log n amortized search cost. How come?
Because S of t is going to be n.
Good. So remember that t is just the root of this binary search tree. So the size of the root is just the number of nodes in the binary search tree, which is n. Right? What on the other, and S of x, x is some node in the binary search tree. So what can we say about x?
S of x is going to be 1.
It's at least 1, right? It might not be a leaf, but even if it is a leaf, it has at least one descendant, namely itself. And so the access lemma immediately gives us a bound of order log n. Right? In other words, this Splay tree, without doing any data structure, without any state maintenance or anything like that, achieves log n search time for each item. Yes?
So when you display something, you're assuming you first found it and then.
Yep. That's exactly right. And well, if you think about it, the display time is equal to the time that it takes to find it, right? Because when you find it, you go down the path. And when you splay it, you go back up the path, doing constant work at each step on the path. Yes?
Is there any intuition for why I use a log rather than any other kind of slowly decaying function besides the nice algebraic properties?
Well, so there certainly are nice algebraic properties. I believe that, I think there is an intuition for why use a log, and it sort of comes back to this divide and conquer process, right? That our sort of goal is to kind of split things by constant factors, which from a logarithmic perspective means kind of a constant decrease as you go. All right, and that will become clearer again as we work through this and as you look through the homework. But let me also throw in some intuition here, again, about what these ranks are doing. Like, what is the meaning of these ranks? So I will claim that rank of x is is sort of the desired height of x in the tree. Right? So notionally, right, if I have, say, a subtree which has n over 2 nodes in it, then from a balance perspective, I sort of want that subtree to be one of the 2 children of the root. Well, if that subtree is one of the 2 children of the root, then the depth of that node is 1. And so the difference in rank between that big subtree and the root is 1. And so the time to find the node at the top of that big subtree is 1. Okay? So these ranks, and again, this is again connected to the logs, right? We sort of, the height of a node is kind of the log of its number of descendants in a perfect binary subtree, okay? Or in a perfect binary tree. All right? So what I'm going to spend the next 20 minutes doing is proving the access lemma without any assumptions about the weights, except that they're positive. Before I do that, are there any questions about, you know, how the Splay tree works or this immediate consequence of it? Yes?
So the costs in those other alternatives to the Splay tree, are they just constant factor increases or are they something worse?
Sorry, the costs in things like...
maintaining that extra state.
Oh, so the costs are constant factor. That is, these alternatives also achieve logarithmic time searches, right?
Is this constant just smaller than those costs?
That sort of is an implementation-specific question, right? I mean, you know, it has to do with the architecture of your computer and so forth. In terms of number of comparisons, I think that Splay trees, I think they have a slightly worse constant. But what's really interesting about Splay trees is not just this log n, but all of the other bounds that follow from the access theorem. So once I've proven that, I'll show you the ways in which this is superior. Yes?
So we splay all nodes, right? All nodes are defined.
Any node that you find, you splay.
So wouldn't it be better if we just didn't splay, say, very small nodes?
Yes. Sorry, not very small nodes,
like
but,
roots, for example.
but there are a number of heuristics discussed in the Splay tree paper and that have been experimented with. So for example, you might say, if it doesn't take me a long time to find something, I shouldn't bother splaying it, right? If the search is fast, then I don't need any potential, so don't waste energy rearranging my data structure. Or maybe I should only splay it part way up in order to have some hysteresis and avoid dealing with temporary changes in my access patterns. And so there are a number of heuristics like this, some of which, a lot of them you can prove don't change things from an asymptotic perspective. And then the question is, do they help in practice? And that's an experimental algorithms question, the kind that you might want to explore in your final project for this class. Okay? Yes?
I don't get what's we haven't done any assumption on the structure of the tree. Like,
You're right.
We just have the operation of splaying.
Yes.
So, what is the splay tree then? It's the tree.
It's the tree that results from all of the splaying that you're doing.
Okay. And in the beginning, like the first input, what?
Good. So you're raising a question, which if we think back to our potential function analyses, there was this issue of the starting and finishing potential.
Yeah.
Okay. So when we talk about amortized time bounds, right, we have this nice telescoping of all of the intermediate potentials, but we still have to worry about the starting potential and the finishing potential and differences between them, right? And I'm going to have to do that for the Splay trees. I'm going to have to think about the starting and finishing potential and ensure that I take that into account when I give these bounds. But let me defer that until after I prove the access lemma. Okay. All right, good. Everybody's happy now? Let's start proving the access lemma. So to prove the access lemma, the way we're going to prove the access lemma is by analyzing one double rotation. Okay? And I'm going, right, so what we want to prove is that the amortized cost is the difference in ranks between the root and the node that we start splaying. So if I can just prove that in each rotation, the amortized cost of that rotation is equal to the difference in potential between the starting node and where it finishes up, and the node that it's replacing, then I can telescope that argument in order to argue that the total cost is equal to the difference in ranks. Okay. So we're going to analyze one rotation, and we are then going to telescope the analysis to get the result. Okay. And what I want, in particular, what I'm going to show is that if x starts with rank x and finishes, with rank r of x, and finishes with r prime of x, then the amortized cost of the rotation is 3 times r prime of x minus r of x. Okay. So why does that produce what I want? Why can I then use that in order to argue the access lemma? Well, I started with rank x. I do run rotation, and the amortized cost of that is r prime of x minus r of x. The next thing that I do is rotate x again. So now it's starting with cost r prime of x, and it gets with rank r prime of x, and it gets some new rank r double prime of x, right? And I just keep adding up those differences, and in the end I have a telescope between the initial rank of x and the final rank of x, but x will be the root at the end of the splay. Sorry, I should fill that in a little bit. So the total cost is now going to be equal to 3 times r prime of x minus r of x. That's the first one, plus 3 times r double prime of x minus r prime of x, plus dot, 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 plus 3 times r final of x minus r almost final of x. Sorry, this sometimes mathematical notation is more confusing than it is helpful. So when we sum these all up, we get that the total cost is 3 times r final of x minus r initial of x. But what is r final of x? Right? We finish with x at the root, right? So this is equal to 3, and the rank of the root is just the log of the total size of the tree. So that's r of t. Right? So that's all of the rotations of x. At the very end, x might be a child of the root. We can't do a double rotation at that point. So at that point, we may have to do one more single rotation. That's where we're going to get our plus 1. So that's the structure of the proof, to just analyze a single rotation. And so what I'm going to show you is an analysis of there's two kinds of double rotations. The analyses are similar. I'm going to show you the more difficult one, the zigzag. You can look at the zigzag in the paper. It's done much the same. So we have this zig-zig operation where we start with these, with this structure of tree, and we finish with this structure of tree as we splay x up. So I'm going to use r to denote the ranks of this tree, and r prime to denote the ranks for the finishing tree. All right. So the first question is, which nodes change rank? Because after all, the potential is the sum of ranks. So if a node doesn't change in rank, then it's not contributing to a change in the potential. Yes?
X, Y, and Z.
Only x, y, and z. So in fact, the change in phi is equal to r of x, sorry, do it the other way, r prime of x plus r prime of y plus r prime of z minus r of x and r of y and r of z, right? We also have the real cost. And the real cost, we're going to measure it in rotations. So we're going to say that the real cost is 2, because we do two single rotations. Okay? But we can use whatever constant we want. Okay? And we need to argue that in an amortized sense, the change is basically the difference in ranks between the rank of the whole subtree and x's rank down here. So again, let me start with some intuition. Okay. In which directions are the different ranks changing? Which ones are going up? Which ones are going down? By how much? Good. So x is rank is increasing. Z's is decreasing. And from an intuitive sense, I'm going to say that y is unchanged, although of course that won't fly for a formal proof. Okay? But y is sort of still in the middle somewhere, so let's just think of that as being as not being changed. So what kind of things might happen? So if if the rank of x increases by a lot, okay? In other words, r prime of x is much larger than r of x. What does that tell us about the shape of the tree? Well, in that case, 3 times r prime of x minus r of x, which is the thing that we want to bound, which is our claim bound, is much greater than 2. Right? In other words, if the rank of x goes up by a lot, then in a sense, the change in potential is going to sort of cover it's going to sort of absorb the real cost. So what I'm saying here is that if we have a case where the change in potential is very large, in other words, where the claimed amortized cost is very large, well, it's fine. Claiming an amortized cost is very large is easy, because you can just sort of swallow up the real cost as part of this large amortized cost that you're claiming. Sorry, yes, go ahead.
Why is the real cost 2?
Oh, that's the definition. We're measuring our cost in terms of, say, pointer changes or single rotations, right? So when I do this, my real cost is to move x to y and then to move it to z.
Okay, but we're not tracking all the changes in the tree.
But those are all the changes in the tree, right? That's the thing about this rotation, is that the only pointers that I have to change in order to change from this tree to this tree is I have to change the 4 pointers hanging off of x, y, and z.
Right, okay, I was counting 4.
Right. So again, it's a constant. It's just a matter of changing units. So I'm thinking of it in terms of how many single rotations I did, but you can measure pointer changes instead if you like. Okay. So if the amortized cost of this rotation is huge, then we're kind of in good shape. We don't have to worry about the real cost. The worry is, what if it doesn't increase a lot, right? What if r prime of x is almost the same as r of x? So then we have a worry, because we're claiming an amortized cost that is very small, but our real cost is very large. So how can we justify claiming a small amortized cost if we have a large real cost? Where is our data structure getting better in a way that justifies that claim? So again, structurally, what does it mean for r prime of x to be almost the same as r of x? Yes?
Then the size of the other of y and z had to find out?
The sizes of y, yes. Yes, you're absolutely right. Right? So but can we unpack why the sizes of y and z go down if x has roughly the same rank after the rotation?
Y loses the rank that it got from x.
Yes.
And
So what's the shape of this tree? I'm telling you that the rank of x, or the final rank of x, in other words, the size of this tree, is roughly the same as the rank that it had at the beginning. So what does it tell us about the tree? Yes? X is really big, right? Almost all of the weight of this tree is under x. Okay. Okay. So that's when we don't get a large increase in potential, is when x already had all of the children. But that means x was fat. So that means that we're doing exactly what we know is a good idea. We're taking a fat node and we are promoting it in the tree. And that is a way to make the tree better. We're improving the balance by bringing the fat nodes up. Okay. But as you said, because x is fat, that means that y and z have dramatically smaller ranks when we finish the rotation. So I'm going to keep these rotations around so that we can talk about them. But now we'll do the formal proof. Math. So first I'm going to simplify, right? So my amortized cost is equal to 2 plus r prime of x plus r prime of y plus r prime of z minus r of x minus r of y minus r of z. So what's the first obvious simplification that I can do? Yes?
Rank of y is rank prime of y?
Rank of y versus rank prime of y. Let's be a little careful about that. So how do we define rank of y and rank prime of y from these trees? Basically, the rank of y is determined by what subtrees?
The subtree roots at x and subtree c.
Yeah, exactly. It's the subtrees A, B, and C, along with node x. Now, after the rotation, what is the rank of y determined by?
B, C, and D.
B, C, and D. Same subtree? Not exactly, right? It's lost A, it's gained D. So we can't claim that y is unchanged. That's what I was claiming in an intuitive sense, but it's not actually true. So we have to be more careful now that we're doing math. All right? So what simplification might we pull off? Yes?
So the roots have the whole tree, so the new x is the same as the old z.
Exactly. If you look at this, I shouldn't have lifted it back up. Over here, rank of z was the log of the size of the whole tree. Over here, the rank of x is the log of the size of the whole tree, or in other words, rank prime of x. So those two quantities cancel, right? So I can get rid of r prime of x and r of z. Okay. And now I'm going to do something which was not obvious but is helpful. I'm going to upper bound this quantity. Instead, so I'm going to did I cancel the right thing? Yes. So over here I have an r prime of y and an r prime of z. But I'm going to be sloppy, and instead of talking about y, I'm going to talk about x. All right? So again, y is the confusing one because it's changing, and so I'm going to try and take it out of the equation. So instead of thinking about r prime of y, I'm going to put in r prime of x. Why is that a legitimate upper bound? Because x is above. Okay, so now we have r prime of x plus r prime of z. And now I want to play the same trick over here. And so I'm going to subtract off r of x because it's already there. But what can I do to get rid of this r of y? I hear disagreement. Okay, who can shout louder? So what should I subtract off if I want an upper bound? Oh, still disagreeing. Stop and think. What is it? If I want an upper bound, can I subtract off something bigger than my quantity or smaller than my quantity? Smaller. So what is smaller than r of y? Remember, r is over here. Right? R prime is over there. Over here we have r. R of x. Right? Good. Okay. So what we now have can be written as 2 plus And so we're going to have an r prime, and I'm just going to rearrange, r prime of z minus r of x. That's one of the r of x's plus r prime of x. What was that? Yeah, remember, we canceled this r of z against this r prime of x. All right. Now, you'll notice that this quantity is what we actually want in the potential in the amortized cost, right? Our claim is that the amortized cost is 3 of these. Here we've got 1 of them. So it's sufficient to prove that 2 plus r prime of z minus r of x is less than twice what we want, r prime of x minus r of x. Okay. Happy with that? So, writing this a different way, you'll notice how I'm looking at my notes a lot now because I'm much better at intuition than I am at math. So here we have r prime of z plus r of x minus 2r prime of x is less than or equal to minus 2. So that's just rearranging the terms. Okay. And if I now go back to sizes, if we go back to the definitions of the ranks, right, sorry, let me unpack this again to make it nice. This is r prime of z minus r prime of x. That's going to be one thing we look at, plus r of x minus r prime of x. And I want to prove that that's less than or equal to minus 2. But what are these quantities? Well, if we go back to this as being defined by the logs, this is equal to the log of s prime of z over s prime of x. And here we have the log of s of x over s prime of x. Okay? So this is all sort of magic math, right, that ends up with this formula. And we want to prove that this is less than or equal to minus 2. Okay? So how do we argue that this is less than or equal to minus 2? Well, now we can finally surface from the math and look at the pictures again. So what are these quantities? Where are s prime of z, s prime of x, s of x, and s prime of x in my pictures above? Okay, so let's circle the subtrees that we're talking about, right? So which subtree corresponds to s prime of z? That's this guy over here, right? Whoops, sorry. Here's s prime of z. Okay, and where is s of x, the other thing that we needed? Yes? Sorry, this is, I don't have enough resolution on your finger to. It's over here, right? Okay. Now, what's interesting about those two subtrees? They're disjoint, right? They're disjoint and they cover everything, right? Except for one node, but right, except for node y, but they're disjoint. So the point is that this is equal to the log of some quantity a plus the log of some quantity 1 minus a, right, where a is between 0 and 1. Right, so a basically is saying what fraction of the tree is a and b, and what fraction of the tree is c and d. Right? Okay, and so what can we say about log a plus log 1 minus a? Well, that's one of these concave functions, right? It's sort of maximized when a is equal to a half. And when a is a half, and you take the log of a half plus the log of a half, then this quantity, log a plus log 1 minus a is equal to minus 2, as we claimed. Boom, right? There's the answer. Okay. Any questions? I'm sure everybody followed all of that math exactly and understands exactly what was going on as we did those equation manipulations. Yes?
So we don't actually need to like prove that it's like at most -2. It just needs to be like at most some negative number.
Yeah, exactly. If you proved it was some other constant, you would still be fine. Right? We would then just need to change the units on our potential function. So we could use count pointers instead if we wanted to. Other stuff? Okay. Yes?
Why did we ignore the weight of y?
Well, we are ignoring the weight of y, but in the sense that we're analyzing upper bounds that include the weight of y. Right? In other words, when we went over here and we replaced r of y by r of x and took an upper bound, we're not ignoring y. We're not ignoring the weight of y. We're just getting y itself out of the equation by looking at an upper bound instead. Okay. Other questions? Yes?
Where did the less than or equal, like in the first amortized cost, less than or equal to 3 r of t? No, all the way on the right. Where do you get like the O of log S of t over S of x?
Well, remember that r of t is defined as the log of s of t.
Oh, okay.
Right? So this is just plugging in the definition of r of t.
Okay.
Yes?
In terms of implementation, if you want to take advantage of this telescopic sum, we first need to find x.
Yes.
And then start doing the double.
Absolutely.
But the goal is to find x just in the search.
Yes, but so again, notice that the cost, the real cost of doing the splay is equal to the length of the path, right?
Yes.
And that's also equal to the cost of doing the search. So if I've told you that the amortized cost of this, I can sort of swallow up the cost of the search as another constant multiple of the cost of the splay, right? So searching is covered by splaying, and splaying now has this small amortized cost that we've just proven. Okay? Good. So now we've proven the access lemma. And that gives us the bound that we wanted of order log n for doing a search by taking weight equal 1 everywhere. But now we do have to address this issue that was raised. I want to leave that up since we're going to use it. What about the starting and finishing potentials? So now we can say that the amortized cost of a sequence of operations, right, is equal to, or sort of upper bounds, the sum of the real costs plus this change in potential between the start of all of your operations and the end of all of your operations. Yes?
I have a question. We just talked about the zigzags.
Yes.
Want to talk about the zigzags or?
So the analysis for zigzag is done almost exactly the same way. And so you can look at it in the paper if you care to. You know, I don't think that you get a lot of additional value out of seeing a different set of random mathematical manipulations, which is why I don't want to show it in class. Okay? But it's easier. It's easier because, I mean, again, pictorially it's sort of easier because you can sort of see that you're making a more balanced tree. Right? Okay, so what about this, this delta phi term, right? So in other words, if from beginning to end there's this there's this huge change in potential, then maybe we don't actually have a good upper bound on the real cost by looking at the sum of the amortized costs. We may be cheating and putting a big extra number in that we're not counting. Okay? But the question I'm going to ask is, how big can that number be? Okay, so what is the maximum delta phi that we have to worry about as sort of a correction in our amortized analysis? Okay. So if I'm going to ask you for the maximum change in phi, how do you upper bound that? How do you figure out what the worst possible change in phi could be over a whole sequence of splay operations? What would produce the absolute worst change in phi? not yet looking at the specific potential function, but just in general terms, if you have a potential function, what produces the very worst change in the potential function going from a start to an end? Maybe that's one of those questions that's too easy. Yes?
Start with a really small one and get everything.
Exactly. The worst thing is if you start with the smallest possible potential that your system can have, and you finish with the largest possible potential that your system can have. So that lets us unpack the question into what is the maximum possible phi for our system, and what is the minimum possible phi for our system. So how do we answer those questions? And this is for a given set of wi's, a given set of weights, wi. How do we write the maximum and minimum phi in terms of those weights? And we're just trying to give bounds here so we can be kind of sloppy if we want to. Yeah?
Well, the maximum, if all the weights are the same, you're just going to be a straight line.
So I don't want to say what weights give you the worst phi. I want to say you pick the weights. Now what tree gives you the worst phi? Right? Because we fixed the weights for the analysis. So the question now is, for those weights, what is the biggest change in phi? Yeah. One each. I have a synchronization error.
Only you do it. Who's going?
This is the thing. If you have your weights, you may do a line with the heaviest weight at the bottom.
Good. So yeah, you can imagine putting the heaviest stuff at the bottom and going all of the and then going up. But I'm going to be even more pessimistic than that. I'm going to say, suppose that everything is under everything. Okay? So if I write W equal to the sum of the wi's, okay, the size of the whole tree, okay, then certainly the maximum phi is at most n times the log of W. Right? Because each node can only have W underneath it. Right? Okay, now what would be the corresponding argument about the minimum possible phi? No, it's not 0, and that's actually very important. Yes?
Big W if nothing is under anything.
So if nothing is under anything, then nothing gets big W. Right? Because W is the sum of all the weights. But I still get something, and it's very important. Yeah?
N times the sum of the logs of the wi? Or sorry, just the sum of the logs of the
Exactly. So the point is that every node has itself as a descendant. So even if it has no other descendants, its size is wi. And therefore, its potential is at least log of wi. So we have at least some of the log of the wi's. Okay. So notice here we have n log w's, and here we have n different terms, each involving a wi. So I claim that the maximum change in phi can be written as the sum of the logs of w over wi. Right? I have these n terms. I take a log w for each term, and I take a log wi in each term. I'm subtracting, so I get this ratio. Okay? Now, going back to our sort of amortized bounds, what is log of w over wi? If we think of it, how might that emerge from doing an amortized analysis of an operation? What operation would produce this cost? Right. So this is equal to the amortized cost to splay leaf I to a root. There's an O in there, right? So my error term, the thing that the amount by which my amortized bound may be off from my real bound, is upper bounded by the cost of splaying each node to the root. So what this is saying is that if I do, in fact, over my course of operations, splay each node to the root, then my amortized cost bound becomes valid. Right? So if I just take a tree and do a single operation and say the amortized cost for that is log n, well, then I'm lying, because there is this additional n log n cost in the change that could arise from the change in potential. But once I have done n log n work, then this error term is swallowed up in the work that I've already done. And so at that point, I can sit back and say, OK, my amortized bounds are valid. They provide a bound on the total real cost of my accesses. Does that make sense? If it doesn't, ask a question. Yes?
Should be a lot simpler to it.
Yeah, I put an O. That's good enough. Right? Yes?
I guess my question is, with this sort of data structure, if you had an adversarial opponent, could they somehow get cause to do much more work than they need to do?
But see, that is exactly the perspective of this data structure, is that you do have an adversary, right? The user is the adversary. And as I said, we sort of take the sysadmin's perspective here, that the user of the computer system is evil and trying to make our lives difficult. But the analysis that we've done here shows that they can't, right? We have proven that no matter what they do, our amortized cost is small. Yes?
Doesn't the amortized cost not provide a bound, it don't defeat negative?
Yes, but that's just it. Sorry, I mean, I should put absolute values in things here, but the magnitude of the change in potential is upper bounded by this.
Okay, so it's only a problem when it's negative, and in both negative it could get you, so it can.
Exactly, exactly. All right, yes?
It's a leaf, but maybe it's not a leaf.
But that only helps us. Sorry, sorry, no, sorry. I'm not saying that we have to actually splay each leaf. I'm saying that we have to add in an error term that says, well, as if we splayed each leaf, right? As if we splayed each node from a leaf, that there has to be an error term there in our total bound. Okay? Yes?
I guess I'm just not understanding something in general. So like, for other data structures, what we usually did was we started with just zero potential. And
Yes,
added things in.
that's right. And why couldn't we do that here?
Are we just starting with random trees?
So the analysis that I've done so far just says, start with any tree, do a sequence of operations, what's the amortized cost? And if we just start with any tree, then we're not starting with a zero potential. But that takes me to, I mean, I have 5 minutes left, and I did want to cover what about insertion. But actually, before doing that, let me show you one other cool result out of splay trees. So we did an analysis that used uniform weights. And from that analysis using uniform weights, we were able to conclude that this was as good as any balanced binary search tree. But let's think of something else. So now I'm going to show you something called the static optimality theorem. So suppose that I now tell you that I have this set of n items, and I know how often each of them is going to be accessed. Or I know the frequency at which they're going to be accessed. Okay? So I tell you that item I has access frequency pi, where that is something between 0 and 1. Okay? So you could imagine that you would want to leverage that information, right? If you know that an item is going to be accessed often, you could put it at the root, and then its accesses would be fast, and so your average access time would go down. And you could imagine taking these access frequencies, pi, and building an optimal static search tree. Which puts, I mean, there's sort of a tension. This is kind of like related to Huffman coding, where you want to put the most access stuff at the top, but you still have to obey the ordering relationships on the items. So you can't just put the frequently accessed stuff at the top. You also have to worry about how that moves other stuff around. But you can ask, what is the optimal search time that I can achieve from a static binary search tree? Okay? And it turns out that the answer is your average access cost is order of the sum of minus pi log pi. Anybody seen that formula before? Okay, so that's the entropy. And actually, from a binary search tree perspective, it kind of makes sense. If you think in powers of 2, right, you can have at most one item that's accessed half the time, and so you should put that at the root. You might have 2 items that are accessed a quarter of the time. You should put them as children of the root. And so basically, you could put the depth of an item to be equal to the log of its access frequency, and you'll achieve this as the average access time. Okay. Now, the remarkable claim is that a Splay tree amortized access cost is order minus the sum of pi log pi, even if the pi are unknown. Okay? I mean, the Splay tree doesn't have any place to store the PIs. It doesn't have any way to know the PIs, right? And nobody may know the PIs. It just may turn out after the fact. But after the fact, you can go back, you can look at the PIs, and you can see, oh, my Splay tree matched the optimal static data structure. How do we prove this? Well, all we have to do is go back to the access lemma. Okay? Just set wi equal pi. Okay? Then our access theorem says that the amortized cost is equal to the order of the log of the sum of pi's over pi for accessing item I. And this is just one, so we're done. Boom, right? Okay. Let's try it another one. Another trick that you might try to do in practice is keeping around what's called a finger. So this is the static finger theorem. Suppose you've got a binary search tree, but you know that all the accesses are going to happen somewhere specific in the tree. There's locality of reference. So what you can do is maybe you should start your search from there, right? So instead of starting from the root of the tree, start your search from some other node of the tree. And if the item you want isn't in the subtree where you started, then you may actually have to go up to find it somewhere else in the tree, and that counts towards your access cost, right? But you could imagine that, again, you have your search tree, and after the fact, you say, oh my god, all of the accesses were in that part of the subtree. I should have put a finger there. Okay. Well, the claim is that Splay trees beat the best static finger. And how do you prove that? Well, you set the weight of a node to be equal to 1 over 1 plus the difference in position in the tree between the node and the finger squared. Whoops. Squared. And then it falls out of the access lemma. Okay. There's also something called the working set theorem. Okay. So you can imagine keeping a cache around, all right, of the recently accessed items. And instead of using your great big binary search tree to find the items, you would only have a search tree on the k most recently accessed items, and you would do a binary search tree on just those k most recently accessed items. So if your item was among the k most recently accessed, then you could find it in log k time instead of finding it in log n time, right, which would be a lot faster. Okay. Well, the working set theorem says that if there were t items accessed since the last access to x, then your Splay tree finds the item in order log t time. Okay? So the Splay tree does just as well as if you carefully set aside a cache for your items and searched in the cache of recently accessed items for all notions simultaneously of recent, right? You don't have to specify what t is, but the Splay tree manages to match the caching. Okay? And then you take this whole board and you state what's called the unified access theorem, which says, suppose that after all of your work was done, you went back and figured out which of the 4 of these techniques was the best for your particular access sequence. Well, the Splay tree does better than that. Okay? So this leaves us actually with a really interesting conjecture, which has been around right from the beginning and is still open. And that is the dynamic optimality conjecture. So the dynamic optimality conjecture says that if you look at a sequence of accesses to a binary search tree, there's some set of rotations that are the best possible set of rotations that you could do looking back on those accesses. Like if you knew in advance what the accesses were going to be, then when an item was searched for, if you're not going to ever search for it again, you would leave it at the bottom of the tree. But if you're going to search for it again, then maybe you'd bring it up to the top of the tree, except you'd have to worry about what other things might go down as a result. So you could imagine sort of optimally planning the rotations of your tree to get the very best possible search time for all of these items. Okay? And the dynamic optimality conjecture, and it is only a conjecture, says that splay trees achieve optimality. Or I should say order optimality. So there's certainly going to be a constant factor versus the best possible thing. But the conjecture is that splay trees just are the best possible data structure. Now, how, which I believe because they're so beautiful, right? But how could you prove this? This is a very mysterious question. We'll have some tools for it when we study online algorithms in the later half of this semester. There has been some progress. Right here, one of my colleagues, Eric Demain, developed something called tango trees. And they are order log n times optimal. So whatever the optimal sequence of accesses is, an optimal set of rotations, they spend at most log n times as much as the optimum. So it is possible to prove something like dynamic optimality. They had to make a somewhat messier data structure in order to do it. There remains this holy grail of proving that this one beautiful data structure, which has no state except for its fundamental ordering state, is in fact an optimal data structure. And whoever achieves that's going to get a lot of kudos from everybody. So I'll finish the subject matter there. I will look at insertion and deletion on Monday. There are going to be office hours being held, as I announced, 4 p.m. today and Monday. Where are they going to be held today, TAs? G5, the G5 lounge of the Stata Center. And so I'll see you on Monday.